everyone, this is Akanksha and welcome to our Mechanistic Interpretability 101 playlist. Let's continue our journey into understanding the foundational concepts of neural networks in order to demystify their workings, that is, interpret them. So far we have covered a lot of prerequisite topics in this series, and today I want to talk about the crux of the matter, that is, the building blocks of neural networks. This episode and the next few episodes are going to be focused on the parts that make up a neural network and the mechanisms behind them. So we will talk about weights and biases, activations, backpropagation, loss functions, optimizations, and all of that. So imagine these building blocks to be pieces of the jigsaw puzzle. We know how the pieces connect mechanically, how the tabs fit into the slots, what material they are made up of, and how to assemble them. Similarly, we can perceive weights, biases, and backpropagation, but in mechanistic interpretability, we are trying to understand something deeper. Why the puzzle assembled itself into this particular image rather than any other? What internal patterns guided its formation? And how each piece contributes to the meaning of the final picture. So in today's episode, let's start by looking at one of these fundamental pieces, weights and biases, which form the basic computational units of a neural network. Before we get into any depth of this neural network ocean, let us take a moment standing at the shore of this ocean and try to absorb this ocean's evolution. Neural networks are potentially one of the major inventions made by humans, like up there with fire, wheel, electricity, and laws of physics and stuff, in my opinion. In whatever us humans invent, I think there are two motivators, two basic primary human emotions. Inventions happen either out of curiosity or out of need. For example, in the late 16th century, we invented telescopes to explore and understand the cosmos, leading to groundbreaking discoveries about our solar system and beyond. Then, more recently, the LHC was built by CERN to explore fundamental questions about particle physics, driven by the desire to understand the fundamental forces of nature. And we invented language, possibly because we needed a communication medium for better survival. And more recently, we invented the COVID-19 vaccine in an urgent need to prevent and control the spread of the virus and protect public. So out of these two motivators, the curiosity and need, I believe the invention of artificial intelligence or artificial neural networks came out of human curiosity about human brain. Early philosophers pondered about human cognition, and some suggested that reasoning could be thought of as a computation. In the late 18th century, scientists discovered that the brain consists of individual cells that communicate through junctions using both chemical and electrical signals. Here we can see a simplified version of how the human brain is composed. Signals come through dendrites, get processed in the soma, which is like the cell body containing the neuron's nucleus. Then they travel down the axon, which feels like a long fiber, and then finally they are passed to other neurons through synapses. In 1943, McCulloch and Pitts created the first mathematical model of a neural network inspired by the basic observations about how biological neurons work, whether they fire a signal or not, based on the incoming signals from other neurons. And thus began the artificial intelligence journey. Let's look at this basic mathematical model of an artificial neuron, which is a simplified version of what we just saw in the biological neuron. So in this model, the x, that is x0 through xm, are denoting the inputs, similar to the signals received by dendrites. These inputs can be anything, from images or videos to make a car autonomous, numerical data consisting of historical prices, current indicators, and volume in the case of stock prediction networks, and audio data in the case of a translator network. And as we saw in the linear algebra episode, all of these input data points are vectors, arranged in matrices for easy computation. So X is our input here. Let's focus on W now. W is our weight. W0 through Wm are going to be our weights corresponding to all the inputs X0 through Xm. These determine how important each input is. And then the Y represents our output, like the signal sent through an axon. Key operation here is surprisingly simple. We multiply each input X by its corresponding weight W and add them all up. So just like a biological neuron decides whether to fire based on its inputs, this artificial neuron processes multiple inputs into a single output through this weighted sum. This is the fundamental building block that, when combined with many others, forms the basis of modern neural networks. Though this is a very simple mathematical model as compared to its biological counterpart, it is powerful enough to be the foundation of many AI systems that we use today. This simple neural network is also known as perceptron. It could only solve linearly separable problems. It couldn't handle nonlinear problems like XOR, exposing its limitations in learning complex patterns. So, because perceptrons struggled with non-linearly separable problems such as XOR, where a simple linear boundary is insufficient, we needed a network with hidden layers added to it to understand the complex feature relationships in the input data. Thus came this kind of a feed-forward network that allows information to move in one direction, that is the forward direction, through the various layers, and that can approximate complex functions. So we have the inputs coming in similar to the earlier simpler version that we saw, but now each input is connected to each neuron in the hidden layer. We see here that there are two nodes labeled H1 and H2 in the hidden layer. So now each one of these nodes in the hidden layer takes a weighted sum of the inputs shown by this formula. Here, Wij represents the weights that determine how strongly each input Xi influences the hidden node Hj. So after calculating the weighted sum, an activation function like ReLU or sigmoid is typically applied to introduce nonlinearity, allowing the network to learn more complex patterns. We will learn about it in the next episode. For today, we will focus on understanding weights and biases. Similar to the hidden layer, the output node Y takes a weighted sum of the values from the hidden layer, and that is represented by this equation. Finally, the structure that we see here is the actual neural network that is in use today, which works phenomenally well on various complex problems. The one clear distinction you can make is that this one has an intricate web of connections going from input layer to multiple hidden layers and then finally arriving at the output. Why do we need so many hidden layers and such a complex structure, you might ask? This is to understand the underlying context in the input data. For example, some of us tend to get angry when we are hungry. We need to work in layers to understand that I might be acting angry just because I'm hungry. In reality, basically, I'm hungry. So let me grab some food instead of going around snapping at people. This kind of depth comes from learning our behaviors and patterns when we try to focus on something that is not directly visible to us. Similarly, there's a lot of context hidden in the input data that is not directly visible to us, but adding multiple hidden layers allows the neural network to capture intricate patterns and subtle relationships within the data. Each hidden layer builds on the features learned by the previous one, forming a hierarchy of representations. Each layer can learn increasingly abstract representations. For natural language processing, for example, initial layers might capture individual word features, middle layers can learn relationships between words, and deeper layers can understand sentences and context or semantics. These abstractions allow the network to make meaningful inferences and generalize well on the new data. With each additional layer, the network gains more power to model complex nonlinear functions. Multiple layers enable the network to stack nonlinear transformations, which can approximate any continuous function. These kinds of deep networks have been an essential step in achieving the state-of-the-art models like convolutional neural networks for images and transformers for NLP tasks. So by far we have learned about the structure of neural network and how the hidden layers are helpful. Beyond the basic structure of the network we have seen so far, these are the different constituents that make the neural network work the way it does. In today's episode, we will focus on understanding weights and biases in depth and also understand how the parameters of the network are calculated. Let's start with weights. Weights are the strengths of the connections going from one layer to the next layer. And since it's Halloween today, we will look at this example scenario of choosing a costume for Halloween to understand what the weights do. For those of you who don't know what Halloween is, it's basically a holiday in the United States that involves dressing up as characters, creatures, or concepts, often spooky or imaginative, as a way to celebrate and express creativity. So, when you're making a decision to purchase a costume, you're most likely to give a high weightage to its availability. The second factor that can influence this decision will be the cost for most of us. And maybe a factor like color doesn't matter much to us, so we give it less weightage. This weight distribution is denoted with the values 0.8 for availability, 0.5 for cost, and 0.2 for color in this example. These values indicate the relative importance of each input factor. Our brain is constantly calculating the best possible output based on various such factors, and the relative weights that we just saw help in that decision making. And this is exactly what happens in a neural network as well. So mathematically, this decision can be calculated as this equation here. So y is going to be equal to 0.8 into x1, which is availability, 0.5 into x2, which is the cost effectiveness, and 0.2 into x3, that is the color. So we add all these products and that gives us our output. So we are basically multiplying each input with its corresponding weight and then adding them all together. Keep in mind though that the weights can also be negative in value. So for example, if we suspect that a certain costume is going to be trending this year, then those of you who want to stand out and be unique will give this trendiness a negative weightage. So it may have a value like minus zero point -0.6, indicating that the more trendy the costume is, the more likely you are to avoid it. And then our equation becomes similar, but here we take the negative value in consideration while multiplying it with the input. Weights play a critical role in artificial neural networks because they determine the significance of input signals, directly influencing the network's output. Finding the correct value of weights is our training stage. So whenever you hear someone training a neural network, it just means that they are trying to find the weights they can use to calculate the prediction. So essentially, the weights encode the network's knowledge and are key to its predictive power. For example, in a network trained to recognize cats in images, specific weights become tuned to features like shapes, edges, or textures that are common to cats. These weights help in correct identification of cats in given images. Weight initialization is essential for a neural network because it gives each neuron a unique starting point. So they learn different things rather than all doing the same job. By starting with carefully chosen values, the network can learn faster and avoid getting stuck in the local minima, or having values that are too big, that is exploding gradients, or too small, that is vanishing gradients to work with. This way, the network can find the best way to make predictions more efficiently. There are different methods of weight initialization. Most commonly used one is the random initialization, and there is also Xavier and claiming initialization methods that are used. During training, the network adjusts these weights to reduce the prediction error, capturing patterns within the data. This particular process of adjusting weights to reduce the output error is called as backpropagation, and we will definitely learn more about it in the upcoming sessions. For example, when training a network on handwritten digit recognition, backpropagation adjusts the weights to improve recognition accuracy. There's also learning rate, which basically controls the extent of each weight update. A high learning rate speeds up training but risks overshooting optimal values, while a low rate provides stability but can slow convergence and risk local minima. The learning rate must be balanced to achieve efficient and effective training. So for example, in a model learning stock price patterns, setting the learning rate too high might make it jump over important trends, whereas a very low rate could slow down the training process significantly. Then there is also regularization of weights. Regularization is basically a technique that is used to help a neural network learn general patterns rather than just memorizing the training data. When a model memorizes too much, it performs well on the training examples but poorly on the new data. This is exactly what is called as overfitting. To prevent this, regularization adds a small penalty to the model whenever it tries to make overly complex connections, encouraging it to keep things simple. This penalty can be added in a few ways, such as adding a small cost to having large weights in the network, or nudging the model to prefer smaller, simpler connections, or shrinking some weights to zero, or using dropout that temporarily turns off random neurons during training, forcing the network to learn multiple paths to a solution rather than relying too much on any one neuron. There's also weight pruning or sparsity that reduces network complexity by removing weights with minimal impact on the output, creating a more efficient and sparse network without sacrificing performance. This makes the computation faster and reduces storage needs, especially useful in deploying large models. So all these concepts show how critical weight management is to the training, efficiency, and accuracy of neural networks, especially as they learn and make decisions across various complex tasks. Now coming to bias. In our Halloween costume example, bias would be denoted by our inclination to, let's say, get a Pikachu costume as compared to any other costume. This is irrespective of the weights for the cost, trendiness, or the availability in the inputs. In terms of neural networks, this is how bias contributes. Each neuron has its individual bias that gets added to the dot product of weights and inputs. Keep in mind though that this bias value does not change between different examples in a batch. So batch here means a subset of input data that is used for training the model. So bias stays the same across all input feature vectors for that neuron during a single forward pass. This allows each neuron to shift its activation response by a fixed amount, regardless of the individual input data points. Let us look at this amazing interactive blog by Jay Alamer to understand the impact of bias with this example of housing price prediction. So these are the areas in square feet and these are the corresponding prices of the houses. First attempt will be to calculate average price per square foot given this data so that we can apply that to predict prices for the next house. This value here comes out to be $180 per square feet. So using this 180 to multiply input data of total square feet, we can calculate y, that is the predicted output. So this results in our y is equal to wx equation where w is 180 now. So if we plot this on an xy plane where the x-axis shows the square feet and the y-axis shows the prices, we get y is equal to 0.180x as our prediction line. 180 is replaced by 0.180 here for the sake of simplicity on y-axis numbers. Now you can see that the input data that we use to calculate the average price make the predictions have prices that are way off from this line. So when we change the equation of this line, that is the value of w here, the error too gets changed. It increases in some cases and reduces in certain cases. But by only changing the slope here, we cannot improve the error significantly. So we try adding a constant to this equation. So by adding 150, our error goes down to 799 from 2058, which is quite an upgrade. I highly recommend checking this blog. I will add a link to it in the description because you can also play with the values of the weights and the bias and try to reduce the value of error. It's quite fun to play with. So hopefully that example from the blog gave you some idea about how the bias helps reduce the error. Bias vector is an important part of how a neural network learns. It adds a bit of extra flexibility, allowing the network to create outputs that aren't strictly tied to the straightforward combination of inputs. Without a bias, neurons can only create linear functions that go through the origin. However, real-world problems often need the ability to represent nonlinear functions that don't pass through the origin. The bias gives neurons the ability to shift their responses, making it possible to fit to a wider range of functions. During training, the network learns the bias values along with the weights by using backpropagation, as we saw in the case of weights. Backpropagation minimizes the error between the network's predictions and the actual target values. Biases are usually initialized with small values or zeros and then gradually adjusted based on how much they impact the error. The bias helps neurons learn when they should be activated or respond more strongly. So, for example, in a classification task, the bias can adjust the point at which a neuron decides to activate for a certain class. This allows the network to make more accurate decisions about classifying inputs. Adding a bias vector slightly increases the complexity of the model, which helps it capture more detailed patterns in the data. However, this also means that there are more parameters to learn, which may require more computational resources for training. To make computations faster, operations with the bias vector are often vectorized, meaning that they are done in parallel for all neurons in the layer instead of one at a time. So now that we have learned about what weights and biases are and how they contribute in the neural network's process, let us take a moment to look at this linear equation that we have obtained with respect to neural networks. This y is equal to wx plus p. Isn't it similar to the equation of line? Y is equal to mx plus c. This similarity isn't a coincidence. It actually tells us a lot about how the neural networks work, especially in their simplest form. Let's break it down. In the equation of a line, m is the slope, which tells us how quickly y changes as x changes. If m is steep, a small change in x makes a big change in y. This is similar to w in the neural network, which acts as the weight. Just like the slope in the line equation, the weight w controls how much influence the input x has on the output. A higher weight means x has a bigger impact. Then we have c and b, which are called the intercepts. They are like little boosts that let us shift the entire line up or down on a graph. This helps the line fit the data better, especially when we are trying to represent a relationship that doesn't start right at zero. So why is the similarity important? Well, it's because so far we have only been able to model the linear relationships between input and the output, essentially drawing a straight line that best fits the data. This is useful, but it has big limitations because real-world data is rarely that simple. Think of trying to predict something complex, like a person's mood, based on various factors. It doesn't follow a simple, straight line pattern. That's where nonlinearity comes in. By adding activation functions, which we will learn about soon, neural networks can go beyond straight lines. Activation functions introduce bends or curves to the neural network's decision making ability, allowing it to capture more complex relationships. This makes the neural networks much more powerful and flexible, and capable of modeling complicated patterns in the data. Lastly, in this episode, we are going to see what parameters of a neural network means and how they are calculated. So first, let's check some well-known stats. The breakthrough vision model of AlexNet has about 60 million parameters. Widely used ResNet 18 has approximately 11 million parameters. And Inception V1, that is the GoogleNet model, has approximately 6.8 million parameters. And in the language models, OpenAI's GPT-3 made a huge buzz, having a whopping 175 billion parameters. And the current top large language models are in the house of trillions of parameters. Whereas the open source Llama 2 has 70 billion parameters, and there are some smaller models like Phi 3 Mini that have 3.8 billion parameters. So, what does this number in millions and billions actually mean? These numbers, primarily consisting of weights and biases, are the values the network learns during training to capture patterns in the data, making them essential for accurately predicting outputs. So, let's look at this sample network and calculate its parameters to understand it better. Here we have two inputs x1 and x2 and one hidden layer with three neurons h1, h2 and h3, finally going to the output layer. So each input neuron is connected to each node in the hidden layer. So these three connections from the x1 have three weights going to h1, h2 and h3. And this input neuron x2 has three connections going to h1, h2 and h3, which again will have three different weights. So together that is six weights. And there's going to be three biases per neuron in the hidden layer. So for this layer, the total number of values that we need to calculate or adjust is going to be 9. And then when the output of hidden layers goes to y, we have one weight associated with each of these connections, resulting in three weights, and one bias corresponding to this neuron y, which results in the total number of values that need to be adjusted or calculated here, resulting in 4. So total number of parameters for this network are 9 plus 4, that is 13 parameters. I hope this small example helps in understanding what exactly parameters are. So we covered the basic structures of neural networks and learned about weights, biases, and parameters in this episode. I can't wait to discuss the next constituents of neural networks like activations, loss functions, and backpropagations with you. So see you in the next episode. Cheers!